So today I will talk about one advancement or another way of visualizing diagonalization that we are calling it a spectral decomposition, or simply I will talk about matrix decomposition. And what I had mentioned that the first easy decomposition that is based on eigenvalue, we are calling it spectral decomposition. And singular value decomposition is just an extension of a spectral decomposition. Why? You can find singular value decomposition as an application of a spectral decomposition. If you understand a spectral decomposition very well, then there would be no issue to understand singular value decomposition. So in this lecture, I will conclude with spectral decomposition, and I will give an assignment of singular value decomposition as an application of a spectral value decomposition. So directly I am coming to outline of today's lecture. So first I would like to give a recap of diagonalization that I had already discussed in last class. Then I will go to discuss in detail about a spectral decomposition. Okay. Then if time permit, then I will go to discuss about singular value decomposition. Otherwise, I have already mentioned that it is just an application of a spectral decomposition. What a spectral decomposition is only meant for a symmetric matrix. So if you are taking a matrix which is symmetric, that means A equal to A transpose. This is meaning of a symmetric matrix. So it is only for A into A transpose, and singular value decomposition is for any kind of matrix. And here, apart from symmetric, it must be a square matrix. So matrix must for a spectral decomposition, a matrix must be a square. And first condition, second condition is that matrix must be a symmetric matrix. So two conditions you need to apply spectral decomposition. But when you are coming for singular value decomposition, then this matrix A, it may be any kind of rectangular matrix M by N, any kind of general matrix. Okay, so that's why it is more general kind of decomposition approach. And second approach, you know that how you can say that singular value decomposition is just an application of a spectral decomposition. Why? Because you construct a new matrix A into A transpose, because A is not a square matrix, neither it is here this A is a symmetric matrix. But if you define A into A transpose or A transpose into A, then both these matrix happens to be what, square matrix as well as symmetric matrix. You can see that easily. You can verify that what is a transpose of A into A transpose. If you find transpose of A into A transpose, so apply whole transpose. So all these uh, operation you know from high school. So that's where I'm. So what would be into a transpose? It would be simply what is happening. How you define a transpose of two product of matrix. So if you are having two matrix A and B, then transpose of A into B, it would be what? It would be written as B transpose into A transpose. This is the rule of doing transpose of a product of matrix. So similarly, that's way this transpose of A into A transpose, it can be written as A transpose of transpose. So double transpose is always happens to be a dual kind of phenomena. That means transpose of transpose happens to be the matrix itself. So transpose of transpose, it becomes A, and here second this one you will get A transpose. So what you observe that uh, if you do transpose of this, you are getting the same matrix. That's why this matrix is symmetric. Similarly, you can prove that this matrix would be also symmetric. So anyhow, if you don't have any symmetric and positive symmetric and a square matrix, you can always construct a symmetric with these two kind of symmetric and uh, square matrix. So always you can apply a spectral. Then after that, doing this, apply a spectral decomposition. Third concept is a spectral decomposition apply here. So in short, I would like to write it as okay. So that's way I told that singular value decomposition is just an application of a spectral decomposition. So it is all about, if you understand a spectral decomposition, that means you know about singular value decomposition as well. Coming to recap of last class, that means diagonalization or diagonality. That means if you are taking any square matrix and that matrix happens to be that matrix is having an eigenbasis, then we can say that that matrix can be diagonalizable. So those things I had already told that today I will talk about algorithm to establish a diagonalization. So what we do, suppose we are asked to determine whether a given n by n matrix is diagonalizable or not. So if so, so we wish to find an invertible matrix S. Here it would be S such that S transpose AX, it would be a diagonal matrix. So what is S? So in last class I had already told that S is just what? It is a matrix. It is a matrix, invertible matrix, in such a way, consider all the eigen bases as a column form. That means eigenvector of a given matrix, take eigenvector of a given matrix as a column of this matrix, and that matrix would be always invertible matrix. And if you apply this operation S transpose AX, so it would be a diagonal matrix, provided that the given matrix is having any eigen basis. So I had taken two examples where in one example that matrix had a eigen basis, but in another example that matrix had not eigen basis. Those two examples I had already discussed. So a step of derivation is what? First step is that again we need to find eigenvalue of the given matrix. So how we find? By solving this characteristics equation. Okay, then a step two, what we will go, once we are having eigenvalue, then for each eigenvalue, we are defining eigenspace and we are finding that eigenspace. It always happens to be linear span of some basis elements. So that technique always, you know, that means this eigenspace always happens to be kernel of uh, A minus lambda I. Okay, once you are having eigenspace, then matrix, the given matrix, it would be diagonalizable if the dimension of the eigenspaces, it will be add up to n. That means that means size of the matrix. Then we can say that the matrix would be eigenspace. That means simply in another way we can say that the matrix is having an eigenbasis. Then in this case we can find an eigenbasis because we are having an eigenbasis. So that's why we are suppose v1 v2 vn, all these are eigenvector of A, which is forming eigenbasis of given domain Rn for the matrix A. Okay, by now we concatenate those eigenvectors and eigenvector of that coming from eigenspaces, then we will get what? Uh, the matrix S. Directly we will get a matrix S by taking as a column, and what you apply S inverse AS, then what you will see, automatically it will be converted into a diagonal matrix. So very simple kind of scenario is coming here. So this a step, last step you can call it, it is a step 4. So you can write it like a step 4. This is the, so in 4 step always you can observe diagonalization if provided the matrix is diagonalizable. So few example I have taken here, same example, 3 by 3 matrix I have taken it here. So what you do, first step, find the eigenvalue of this one. So it is having uh, actually two eigenvalue. 0 is having it is repetitive in nature. 2 times 0 is coming. That means algebraic multiplicity of the eigenvalue 0 is 2, and algebraic multiplicity of the eigenvalue 1 is 1. So you got two eigenvalue. With respect to eigenvalue 0, you got the eigenspace. So luckily we are getting that eigenspace associated with the eigenvalue 0 is what? It is a two-dimensional space. It is a span by two vector. Call this one V1, this one is v2. So v1 and v2 are, you can say that it is a these are eigenvector of the given matrix A associated with eigenvalue 0. And now with respect to eigenvalue 1, you again find another eigenspace that we are calling it E1. And what is the basis of E1? Is basis of E1 is this vector 1 0 0. So call it v3. So now you can say that v3 is the third eigenvector of this matrix associated with the eigenvalue 1. So you can observe that v1 v2, two eigenvalue associated with a single two eigenvector associated with single eigenvalue 0, and v3 is the single eigenvector associated with eigenvalue 1. So you now by taking these v1 v2 v3, we are taking like this one, and we can bring it together, concatenate these together. So you know that v1 is coming from it is associated with 0 eigenvalue 0, v2 is also associated with eigenvalue 0, and v3 is associated with eigenvalue 1. So we are having three vectors, and what A is what? It is defining a operation over where R3. So that's where these three vector always happens to be linearly independent. So these three V1, V2, V3, it is forming an eigenbasis for R3. So if once it is forming eigenbasis of R3, now we will construct a matrix S. So like this way, this matrix X by considering V1 as a first column, V2 as a second column, V3 is a third column. So in that process, we are getting this matrix. You can observe that. Now, what we do, if you multiply S inverse with A and S, then directly you will get this diagonal matrix 0 0 1. So you remember that v1 is coming in as the first column. What is the eigenvalue of v1? 0. So that's why 0 came here as a first diagonal element. V2 is associated with eigenvalue what? 0. So that's why second diagonal element is again 0. Now v3 is associated with what? Eigenvalue 1. So that's why third diagonal element is 1. So that diagonal picture we are getting it. If you are willing to verify, you can verify easily. The same with this equation also further you can write it. Non willing to find inverse, because inverse is always complicated kind of thing provided the matrix is not orthogonal. So that's why what you do just little bit manipulation of this one. So this equation, matrix equation, how you can write it? Multiply this matrix equation with s both sides. So then what kind of form it will take? To multiply this with s side, s time t, it becomes s into s inverse is what? Identity matrix, because s is invertible. So sd equal to as. The same this equation, matrix equation, can be written like this way. Okay, so verification you can done. So that's why last part I have taken here verification. So verification you can see that when you multiply the matrix, given matrix A with newly constructed matrix S, then you are getting this matrix. Similarly, if you multiply a newly constructed matrix S with diagonal matrix D, then you are getting same matrix. So both here LHS equal to RHS situation you are getting. It seems that whatever we done, it is fine. We have validated. So last step you can call it. This one is the step uh, 5 for validation part of diagonalization. You can call it a step 5. So validation, always try to do validation just for your purpose. It is not for solving problem. It is just for uh, whether you have any committed any whether you have committed mistake or not. So just to find mistake, you need to see that validation part. Okay, so now I'm coming to main part of this course, this lecture, that we are calling it a spectral decomposition. What is that? Okay, so I will talk in detail. So before going to a spectral decomposition, I would like to take few example here and few questions. So you can see it here. When few questions that arises from diagonalization. So uh, when is a given a square matrix is a diagonalizable matrix? Simple question would be there. When every square matrix can't be diagonalizable. So when it would be diagonalizable? So diagonalizable is what? It is very much equivalent to finding eigenbasis. If so, one would like to give an answer that a matrix which is having eigenbasis, definitely it would be diagonalizable. So that answer. And the next question would come, where there is an eigenbasis for, when the matrix will have eigenbasis, which kind of matrix will have eigenbasis. So next question. Then again you have to look for further concept. So how, what are the matrices which will have eigenbasis? Not every matrices may have eigenbasis. So again question will keep on growing. So for which, so simply now once we are having this kind of question, then further question will come, for which matrices is there any orthogonal eigenbasis. Apart from eigenbasis, now we will look for something more, a special kind of eigenbasis. That means orthonormal basis. Which kind of matrices are having orthonormal basis? So it is more tougher question than, or more difficult question than previous two question. Or equivalently, we can say that for which matrices A is there any orthogonal matrix S such that S inverse AS equal to S transpose AX. Why? This is the concept that we know that if S is orthonormal, then what is the S inverse of that matrix? It is simply you may get by doing transpose. So it is, if S happens to be orthonormal. Any question? Any would like to ask? Anyone is having any question? No question. Okay, fine. I'm going forward. If you have any question, then just please ask. I'm going forward. So there are various questions you can after just going through diagonalization and eigenbasis, you are encountering various questions. So definitely one answer is that a spectral theorem. I will say that. So before that, a few more questions I would like to say. Which matrices are simply this question you can repose like this way. Which matrices are orthogonally diagonalizable? That means if a matrix is orthogonal diagonal, what is the relation between A transpose A and A? So suppose if you are having a matrix which is orthogonally diagonalizable, that means you are getting a matrix S which is orthogonal matrix, and you are able to write A S transpose AX equal to a diagonal matrix. Then what kind of matrix that would be? So definitely you will see that here. Suppose a matrix A which is orthogonally diagonalizable, it simply says that there exists a orthogonal matrix S such that uh, you are able to write like this way. This relation is coming in two way, like this way. So you are able to write S transpose A time S equal to a diagonal matrix D. And same this matrix equation further you can write it like this way. If you multiply, we know that S is invertible and inverse, and S is also orthogonal matrix. So inverse of S is what? Just S transpose. So if you multiply S transpose both sides, what kind of form it will take? So reversely you can write it like this way. uh, A equal to S into D into S transpose. That means you have already decomposed this matrix, given matrix A, in the form of S, it is a orthogonal matrix, D, it is a diagonal matrix, S transpose. Further, it is again orthogonal matrix. So you have decomposed the given matrix A in this form. Then what kind of matrix this A? What is that matrix? Actually, that kind of matrix is actually symmetric matrix having this kind of property. So it is always so relation. That's why I have raised one question. A transpose A, it would be equal. If it is orthogonally A matrix A is orthogonally diagonalizable. So this is the concept of orthogonal diagonalization. So then matrix would be symmetric and a square. So that all these question, answer of all these questions, various questions I raised here. The answer of all these questions is what? Simple a spectral theorem. So what a spectral theorem says, or simply you can say that also it is orthogonal decomposition. So orthogonal decomposition or orthogonal, sorry, you can say that simply a spectral decomposition. So a spectral decomposition does just it says that if you are having a n by n square matrix, then it would be orthogonally decomposable or orthogonally diagonalizable if there exists an it is if and if and only if A is symmetric. That means there exists a orthogonal matrix S such that you can write it S transpose AX equal to a diagonal matrix D. It is a diagonal. So if you are taking any a square symmetric matrix, then always you can claim that that matrix is orthogonally diagonalizable. That is the a spectral theorem, or simply you can say that a spectral decomposition. So right now this one is a spectral theorem. So a spectral theorem says that uh, S transpose A S equal to a diagonal matrix, provided that matrix is symmetric matrix. Remember that I have already written. Okay. Now this one is a spectral theorem, and why I'm calling it, it is a spectral decomposition as well. So when you will get a spectral decomposition, that one is actually equivalent form of this spectral theorem. What you do, play with this matrix equation, multiply S transpose with both sides. Then if you, so from here what you will get, you can write A as S time D time S inverse. Okay. So this one is this result we are calling it a spectral theorem. Okay. This This is what we had given matrix A. We decompose it into three matrix. So that's why we are calling it a spectral decomposition. ST in short, I would like to write spectral decomposition. So you may see the equivalency between spectral theorem and a spectral decomposition. This is the criteria. So if you are having a symmetric matrix, always you can orthogonally diagonalize that. That means that matrix S would be an orthogonal matrix. I will take few example. So very simple example here I have taken a 2 by 2 matrix having first row 4 2, okay, and second row 2 7. So we'll find orthogonal matrix for this one, which will decompose the matrix A into very simple matrix, into diagonal matrix. Okay, so that means if you apply S inverse AS over the matrix A, then it will be converted into a diagonal matrix. So what is the step? A step is again similar to diagonalization. First, we would what? We would find a eigenvalue of the given matrix. So what are the eigenvalue of the given matrix? We are getting two distinct eigenvalue. First eigenvalue we are calling it 3. Second eigenvalue is 8. So two eigenvalue we got. Once we are having eigenvalue, we'll look for eigenspace, corresponding eigenspace. So the eigenspace associated with 3 is what we are calling it E3. It is a line with basis 2 minus 1. And eigenspace associated with second eigenvalue 8 is what? It is again it is a line with basis uh, 1 2. So call this one V1. I'm calling this one V2. Now tell me, is there any relation between V1 and V2? One relation you can observe that these two are perpendicular to each other from the graph. It is very much clear. So that means if we consider V1 and V2 as a column of the given column for matrix S, then we can say that we can get almost orthogonal matrix. Okay, so in second form, what in the step 2, what we do, we have to apply uh, some kind of Graham-Smith kind of a technique in order to get orthonormal eigenbasis. So we got eigenbasis as first basis element is V1 with respect to eigenvalue 3, and second basis element is V2 with respect to eigenvalue 8. So V1 is associated with 3 and V3 is associated with eigenvalue 8. So we got eigenbasis. So it is one eigenbasis. So next concept is that what we have to normalize this eigenbasis. We know that we have already done many times that if we are having any non-standard basis, then with the help of Graham-Smith orthogonalization, always we can convert that basis into orthonormal basis. So here one benefit we observe it here, very simple, that u1, if you take a dot product of v1 with v2, what would be dot product? It is 0. So we don't need to apply Graham-Smith directly. What we do, just we need to normalize each vector in order to make it unit vector. So in orthonormal basis, apart from being perpendicular, they must be unit vector. So that's way I'm dividing v1 by norm of v1. So norm of v1 is what? Root 5. So that's why u1, we are getting u1 first orthonormal eigenvector, and u2 is the second orthonormal eigenvector. So we are having now these two are what? These two are orthonormal eigenbasis. So once we are having orthonormal eigenbasis, we are assuming constructing a matrix S where u1 is forming first basis and u2 is forming second basis. So definitely this matrix S would be an orthogonal matrix. And when we multiply S inverse with A times S, then definitely it would be a diagonal matrix where first diagonal is coming with respect to first column of S. What is the first column by S? V1, and V1 is directly coming from V1. U1 is directly associated from V1, and V1 is associated with 3. So that's where 3 we observe here. Similarly, second diagonal element is 8. So that is the concept. So in a step 4, we can directly get a diagonal matrix by doing this operation. So next one, just a corollary kind of theorem here I have taken. So consider a symmetric matrix A. If we are having two eigenvectors V1 and V2 of the matrix, and both V1 and V2 are coming from two distinct eigenvalues lambda 1 and lambda 2. So that means b1 and b2 are not simply, it's saying that okay, so it is not coming from the same eigenvalue. B1 B2 are coming from different eigenvalue. Also, we observe that B1 and B2 happens to be. Then what we will observe, it is very much guaranteed that due to symmetric nature of the matrix A, these two eigenvector B1 and B2 would be orthogonal to each other. Dot product between orthogonal, between those two orthogonal to each other, and that is V2 is orthogonal to V1. So this theorem is just an implication of this example. Okay, I want to go to prove this one. So this I had already taken a 2 by 2 matrix. A was a 2 by 2 matrix. I had already calculated eigenvector V1 and V2, and you had already seen that V1 and V2 happens to be orthogonal to each other. So that's where this theorem is just in an implication of this example. Okay. Coming to further example, I'm taking a 3 by 3 matrix. Okay, it is a little bit complicated. So again, we will find a orthogonal matrix associated with this one, and those orthogonal matrix actually constructed from eigenbasis. So how we can construct that matrix S, and when we apply S inverse A X, then it will be converted into a diagonal matrix. If you are getting that orthogonal matrix, and we know that this given matrix is a symmetric matrix, you can find that it is a symmetric matrix. Here you can easily verify that if you find A transpose of this matrix, transpose of this matrix, transpose would be equal to same matrix. So the given matrix is a symmetric matrix, and also it is a square matrix. So even you might have already seen the definition of symmetric matrix. Always we define symmetric matrix only for a square matrix. Not, we are not generally seeing any definition for a non-square matrix, a symmetric case. So what a step is here? Again, we will follow the same kind of a step. Uh, we are taking in first step, we are finding eigenvalue of this matrix. I had already told that if you observe a singular matrix, by default you can observe that, you can say that this matrix is a singular matrix. Why? Eigen, here columns are repetitive. Here first column has been repeated, second column is equal to first column, third column is equal to first column. So you can simply say that columns are here dependent. One of the eigenvalue, definitely it would be 0. So one eigenvalue is 0, another eigenvalue is 3. Very easy to see from the matrix itself. So you are getting two eigenvalue for this matrix, but here just for just time, save time, I have written here eigenvalues of this matrix. But for your better understanding, always try to solve this characteristic equation and get the eigenvalue just for practice purpose. Okay. In a step 2, what we will do, we will find the corresponding eigenspaces. So take eigenvalue 0. With respect to this 0, we will find eigenspace E naught or E0. So eigenspace of E0, it would happen, so it is a kernel of just this same matrix A, because we know that if you take an eigenvalue equal to 0, then A minus lambda I would be what? It would be A minus 0 time identity matrix. That means it would be the same matrix. That means we are finding the kernel space of this matrix A itself. So what is the kernel space of this matrix? It is actually linear span of these two vectors. First vector minus 1 1 0. Second vector is minus 1 0 1. So call this one V1. That means we are calling first eigenvector V2, second eigenvector. Both first and second eigenvector, it is associated with eigenvalue 0, because this is coming E naught is E0 is eigenspace with respect to eigenvalue 0. So that's way. Now we are having another eigenvalue 3. With respect to eigenvalue 3, we will calculate a eigenspace E3. It is what? It would be just a uh, line. It is a linear span of a single vector 1 1 1. So call this one V3. What? Now, I would like to ask one question, that what is the relation between V3 and V1? Anyone would, anyone would like to answer? Okay. If you are taking time, then I have to answer it. So if you are taking, what is the dot product or inner product between V1 and V3? So inner product between V1 and V3 would be 0. Why? V1 is associated with eigenvalue 0, and V3 is associated with eigenvalue 3. So 0 and 3 both are different eigenvalue, distinct eigenvalues. That's why that previous result what I had already told that. So dot product between V1 and V3 would be 0. Similarly, dot product between V2 and V3 would be also 0. But if I ask what is the dot product between V1 and V2, it may not be 0. Why? Because V1 and V2 are associated with the same eigenvalue. That's why we can't say may here dot product between V1 and V2 may or may not be 0. It may simply, in short, I may write it, it may not be 0 because v1 and v2 both are associated with same eigenvalue. So you can easily calculate this. What is the dot product? It is minus 1 time minus 1 means 1, 1 time 0, 0 time 1. So it is coming, what is this? uh, it is coming here, inner product of v1 with v2 is just equal to 1. That one is not a zero quantity. So easily you can observe that. So eigenvector associated with the same eigenvalue in a symmetric matrix. Remember that I am talking about right now only about symmetric matrix. In a symmetric matrix may not be orthogonal to each other, but eigenvector associated with two different eigenvalue will be definitely orthogonal. You can find the dot product between v2 and v3. Easily you can say minus 1 time 1, okay, minus 1, 0 time 1, 0, 1 time 1, 1. So that means minus 1 minus 1 plus 1. So in result you are getting 0. So similarly you can get inner product of v1 with v3 is also 0. Okay, so that is the rule, that is the benefit of last theorem. Note that the two species are indeed perpendicular to one another. So we can say that E3 is perpendicular to E naught. So here E3 is two dimensional, E naught is two dimensional eigenspace, and E3 is one dimensional, and all these are where in R3. So you can say that E3 is an orthogonal complement of E naught, E0. So simply I would like to write it like this way: E0 is perpendicular to E3. It is happening. Remember that always I am saying that it is happening due to symmetric nature of the given matrix. If this matrix is not symmetric, we can't say all this property. If this property may or may not be true. But if it is symmetric, there is a guarantee that such kind of situation you will get. Okay, so here this eigenspace, it is associated with eigenvalue 0. This eigenspace, it is associated with 3, and the 0 and 3 are two different eigenvalue. So definitely the corresponding eigenspaces would be perpendicular to each other. Okay, coming further, so in step 4, once we are having so our only aim is to find a diagonal matrix and matrix S. That one is directly coming from eigenvector. So in step 3, what we will do, once we have already seen eigen basis, so v1 v2 are coming from eigenvalue 0, and v3 is coming from eigenvalue what, 3, uh, eigenvalue 3. Okay, so we are having 3 eigenvalue. This one is associated with eigenvalue 0, this one is associated with eigenvalue 0, and this one 3 is associated with eigen v3 is associated with eigenvalue 3. So but we see that this is perpendicular to v1 and v2, but v1 and v2 itself not perpendicular to each other. So what we do, definitely this eigenbasis is not an orthonormal eigenbasis. If we, in order to get orthonormal eigenbasis, what we have to do, we have only technique that we are calling it Gram-Schmidt orthogonalization. So we, in a step 3 we will apply Gram-Schmidt orthogonalization over eigenbasis what we got in order to get orthonormal eigenbasis. So here if you apply a Gram-Schmidt process to basis first two basis vector v1 and v2 in first eigen space e naught or e0, what we will get, we will get u1 is just by normalizing v1 we will get u1, and u2 how we will get, u2 we will get by normalizing v2 per, you know that, that means you are projecting v2 in the direction of u1. So this v2 perp is defined as v2 minus inner product of v2 with u1 in the direction of u1. Just so here you are having already v2, you are having v1, so that's why you got u1, and you are having u1, that's why you got all this quantity. And easily if you simplify this result, you will see that the second orthonormal vector u2 is nothing just it is vector minus 1 2 divided, each one is divided by 1 by square root of 2. Just we do normalizing. Okay, so we are having now u1 and u2 as orthonormal basis, eigen basis element. Okay, now we will get third orthonormal basis element u3. How? U3 is totally independent of eigenvalue 0. It is directly coming from it is associated with eigenvalue 3. So that's why just do normalization of v3, and if you do normalization directly you will get u3. So now you are having the three set of vector which is orthonormal. Orthonormal. So that's way. So if you are willing to see the picture of this one, so this one is you can observe that it is e naught or E0. Usually you can say that E0 is what? It is a plane, this plane. And this one is what? E1. E3, it is as what? It is a line associated with eigenvalue 3. Now, after that, what we do? We do normalizing of this one. So this one you can call it U1. This is U1 in the eigenspace E0. This one is what? U2. So geometrical visualization of U1, U2, U3 I have already given. And what is U3? This is the direction of U. It is very easy to find U3, but in order to get U1 and U2, you have to apply grammar with orthogonalization. Okay, because why? Simply U1 and U2 are associated with eigenvalue, same eigenvalue 0. That's why you do that kind of operation. Now we are having once we are having orthonormal eigenbasis, we will go to construct the orthogonal base matrix S by taking U1 as a first column, U2 as a second column, and U3 as a third column. So usually it is a verification. You can do that as is a orthogonal matrix. So what is the verification part of orthogonal matrix? So if you a matrix would be orthogonal, if you multiply the matrix with its transpose, then this multiplication would be always identity matrix. So you do always a verification part whether my result is correct or not. So if you multiply s into s with s transpose, you are getting identity matrix. So this is the verification part. You can check it now. By taking this matrix X, it will diagonalize the given matrix A, the given symmetric matrix A as follows. So if you multiply S inverse with A times S, then you will directly get this diagonal matrix. Easily you can see that U1 is associated with eigenvalue 0. That's why first diagonal element is coming 0. Now, U2 is also associated with eigenvalue 0. That's why second diagonal element is coming 0. And you remember that U3 is associated with second eigenvalue 3. That's where your third diagonal element is 3. So you got these diagonal elements. So all these are very much geometric in nature, and algebraically also you can calculate all these. Okay, next theorem I would like to talk about. All these are simple kind of theorem. These are helping a spectral theorem. So a symmetric n by n symmetric matrix, if it is having n real eigenvalue and then if they are counted with their algebraic multiplicity. So what it simply say that a n by n symmetric matrix always having n number of real eigenvalue if you are counted with algebraic multiplicity. That means in last case what we had in the matrix A, which this matrix having first row, no, first column 1 1 1, second column 1 1 1, third column 1 1 1. So what we observe here, the eigenvalue, we had eigenvalue, first eigenvalue was 0. So we are saying that eigen 0 is coming two times. That means algebraic multiplicity of 0 is 2, eigenvalue 0 is 2, and algebraic multiplicity of second eigenvalue 3 is what? 1. So if you sum up algebraic multiplicity, that means 2 plus 1. What is 2 plus 1? 2 plus 1 equal to 3. That's way. That's way what we can say that why it is happening, because this matrix is symmetric matrix. The given matrix is symmetric matrix. That's where sum of algebraic multiplicity is always equal to n. If it is n by n matrix, So it is right now 3 by 3 matrix, and this matrix is symmetric matrix. That's where sum of algebraic multiplicity is always equal to n. So that this theorem is saying. Okay, so for then I would like to introduce here algorithm for whatever things I discuss, everything I will put in algorithmic approach. That means algorithmic one here I am going to introduce second algorithm of this lecture, that we are calling it algorithm for orthogonally diagonalization. So what is that? In the first step, what you do, find the eigenvalue of the given matrix by solving this characteristic equation. Okay. In the second step, what you have to find the eigenspaces corresponding to each eigenvalue. So how? By solving or by finding kernel space of A minus lambda. So you will get eigenspace. Once you are having eigenspace, what you do? Apply Gram-Schmidt orthogonalization process over the eigenspaces in order to get orthonormal basis for each individual eigenspace. Okay. So in fourth step, what we will do? In fourth step, we will form a orthonormal eigenbasis for the matrix A by concatenating the orthonormal basis of each individual eigenspace, what we already got in step 3. And once we are having orthonormal basis for the matrix A, orthonormal eigenbasis for the matrix A, we will construct a new matrix S by considering these basis element as a columns. So that means S equal to V1, V2, V3. So this matrix, I can say that with certainty this matrix will be always a orthogonal matrix. Okay, when we multiply S inverse with A S, then this resultant would be always a diagonal matrix. So this is the algorithm for orthogonal diagonalization. So you can always do all these calculation. I have discussed everything. Okay, so one example also I had already taken. So one last example I would like to take from geometrical perspective. It is already around 45 minutes. So I won't take much time. Within few minutes I will finish this. So consider an invertible 2 by 2 matrix A, and here a question is that we have to prove that linear transformation uh, T of x equal to Ax, it maps unit circle into an ellipse. And what we have to do, also we have to find the length of the semi major axis and semi minor axis. This would come in term of eigenvalue of this ellipse. Okay. So the special theorem, last theorem, tells that there exists always an orthonormal eigenbasis B1 and B2. Why? Because here is 2 by 2 matrix, so definitely only two eigenbasis element we will eigenvector we will get. So that will form a orthonormal eigenbasis for T. Okay, that would be associated with uh, these two distinct eigenvalue lambda 1 and lambda 2. So because lambda 1 and lambda 2 are distinct, so definitely V1 and V2 will be perpendicular to each other. So that's why you will directly get orthonormal eigenbasis through uh, what we are whatever we had already discussed. So this eigenvalue will be also non-zero. Here, why non-zero? Because I have already taken a condition that this transformation is invertible transformation, because we are mapping from a unit circle into ellipse. So that's why the transformation would be always invertible transformation. You can get back, you can transform back ellipse to a circle. So it is an invertible transformation. So that's where there is no singular kind of concept. There is no zero eigenvalue. So lambda 1 and lambda 2 both would be non-zero. Now, the unit circle in R2, it will be consist of the vector. If you're taking any vector from the unit circle, it would be always what? It is a linear combination of V1 and V2, and linear, this coefficient is coming as a unit coefficient. So cos t. So what is the magnitude of cos t? It will be 1. So cos t times, so that means magnitude of lambda 1 would be 1, magnitude of lambda 2 would be also 1. So cos t times V1 plus sin t times V2. And it's, if you find its image and under this given transformation, what would be image? Again it would be cos t time lambda 1 v1. Why? Because v1 is an eigenvector, so that's why t of v1 equal to lambda 1 times v1, and t of v2 would be lambda 2 times v2. Okay, so you got the all geometry, and with an ellipse, so that image, it is coming where it is an ellipse. And what is the semi major axis? Semi major axis is lambda 1 times v1, and what is the length of that? Length is just magnitude of the eigenvalue. And similarly, semi minor axis would be lambda 2 v2, and would be what would be length? Length would be just modulus of lambda 2. Remember that here I have taken one convention, lambda 1 is greater than lambda 2. That's way lambda 1 b1 where it is associated with semi major axis, and lambda 1 b2 it is associated with semi minor axis. All the geometry you can visualize it here. Regarding attendance, I have already created a link. Go and mark your attendance there. And thank you for attending all these lectures. My suggestion would be that